to. My name is Matt Rolls. I'm the Vice President of Business Development for Specific Energy. And the theme of our presentation today, I think we're going to take about 20 minutes or so of presenting and then leave the rest to sort of questions and comments and open up a discussion. But we're going to talk about our dynamic pump optimizer technology, DPO, which combines the power of edge computing and digital twins to improve pump performance management. And really, as Mary mentioned, what we're trying to do is we're trying to provide a platform that ensures resilience of supply and removes the doubt and the kind of reactive nature sometimes of pump operations by giving utilities the visibility of exactly how their system is operating in real time. The benefits of doing that are intrinsic to the platform itself, such as reducing energy consumption and increasing the asset life of the pumps. But ultimately what the platform is designed to do is to give the operators the visibility they need to ensure their system runs resiliently and efficiently. So just before we start, I know I've mentioned digital twins there and edge computing. Just to put everybody on the same page, a quick sort of summary of what we're talking about there. So edge computing is a distributed IT architecture where the data is processed as close to the originating source as possible. So by operating at the edge, we're able to make those decisions in real time because it doesn't have to go through a series of networks to a data residency, get analyze and then return that back. We do this right at the edge, and you'll see the kind of physical example of that as we move through the presentation. And when we talk about digital twin, this is a virtual representation that serves as a real-time counterpart of the physical process. So essentially what we mean in our terms is we have a complete digital twin of the entire pump system from suction to discharge. So we're able to model that against actual conditions and detect anomalies and suggest optimization. So a quick bit of background on Specific Energy. I appreciate that we may be a new company name to a lot of you on the call, and the technology may be relatively new, but we've been doing this for a long time. Our CEO, Perry, founded the business back in 2010. We're headquartered in Austin, in Texas, but we've been growing rapidly over the last 2 to 3 years with additional offices in the US and myself here in the UK who handles the non-Americas business. We've got over 150 installations of the technology to date with some significant customers such as City of Houston and Gwinnett County. And we have over 2.5 million hours of proven runtime in the field. So as I say, we are not a novel or emerging technology. We've been doing this for a long time with a lot of data and a lot of good references to support that. So I always start with the analogy of a car dashboard. And the reason for that is it's something that should be familiar to pretty much all of us. Most of us drive cars, most of us understand how a dashboard works in a car. But more importantly, when we're taught to drive the car, one of the first things we're taught to do is not to run the car into the red zone. And the reasons for not doing that is that it's bad for fuel efficiency, but it's also bad for the health of the engine. That car is not going to last very long if it's continually running the red zone. And the same is absolutely true with pumps. And in fact, centrifugal pumps have 2 red zones, one either side of this narrow green band that we call the preferred operating range, which straddles a pump's best efficiency point. And just like your car, if you run that pump too fast into the red zone to the right here, not only does your efficiency suffer significantly, but the pump is also susceptible to premature failure through cavitation, through failure of bearings and seals. And also, if you run it too slow, you run it to the left of POR here, you can see again that efficiency suffers, and the pump is also susceptible to damage and failure through excessive vibration and recirculation cavitation. So it's very, very key to the health and efficiency of that pump that it's run in its preferred operating range. However, doing that is not as simple as straightforward as it sounds, because the preferred operating range is a moving target over time. You can see here, this light blue line at the top is a pump's factory curve, and the grey zone here is the POR associated with its factory new condition. But a pump's factory curve is really only applicable on the day that that pump is put into service or shortly thereafter, because as soon as that pump begins its operational life, it becomes susceptible to degradation and wear and tear through debris and through sort of harmful items that come through the pump itself. So fast forward 2 or 3 years, and you can see now that this dark blue line is the current tested curve of that pump. And you can see that the preferred operating range has moved down and to the left. So what this is sort of compounding the difficulty of keeping a pump in POR, because it's a moving target over time. As a result, this is something that we see as the norm rather than the exception. This is a variable speed pump that's installed in parallel with some fixed speed pumps at a big pump station down in the Texas area. And this pump here was operating within its preferred operating range just 39% of the time. So 60% of the time, this pump was being operated outside of its preferred operating range. So it was being operated in a manner that was harmful to the health of that pump, and in a way that wasn't at all efficient. And in fact, you can't see because of the consolidation of data points, but around 15% of those data points meant the pump was operating at shut-off head, not because the pump was operating against a manually closed valve, but the operators were effectively using this variable speed pump as a dimmer switch. They were ramping it right down just to make up for small changes in flow. And they had no indication they were doing anything wrong, other than the fact that they were tearing through this pump and having to have it replaced pretty much once every year, and it was costing them an absolute fortune in wasted energy and pump repair costs. So this was the type of challenge that Specific Energy was created to address, and our company name comes from the definition of specific energy in relation to pumping water, and that is, simply put, is the energy consumed per volume pumped. Or in even more simpler terms, specific energy is power over flow. So when we talk about minimizing specific energy and maximizing energy efficiency, we talk about the pump system in its entirety. We're not just focused on the flange to flange of the pump and trying to make sure that we keep it on that best efficiency point, because there's many other factors in that pump system that affect the overall energy efficiency. So we model the entire system, as I mentioned earlier. So we know the specific energy associated with the static lift. You can see this light blue area here. There's known specific energy associated with the dynamic losses through the pump and the pipe work and the fittings, etc. We know there's efficiency losses in both the motor and the VFD, these curved shapes here. And as we've seen from the previous slide, the real wild card is the pump, the green zone. It's wildly inefficient to the left, and it's wildly inefficient here to the right. What you would expect to see is the narrowest part of that green zone is where the pump's best efficiency point is. But as I mentioned, we're looking for the best efficiency of the system, the minimum specific energy consumption. And that is the lowest point of these U-shapes, or these parabolic curves. And it's worth bearing those in mind, because you'll see them a little bit more as we get through the presentation. So to put this into the context of an operational challenge, let's assume we had a pump station here with 5 pumps. If these pumps are on fixed speed, they would only have 2 modes of operation. They're either on or they're off. So across those 5 pumps, there's a maximum possible operating combinations of 32. But with the recent advent and uptake in variable frequency drives, let's assume these pumps had VFDs on them, and those VFDs were adjustable over a 15 hertz range at half hertz resolutions. You've just taken those 32 possible operating combinations, and you've now got more than 28 million. So quite frankly, that becomes impossible for any manual operator to find the best point of operation within there and to make sure that the pumps are operating correctly. Putting those 28 million operating points on this flowchart here, you can see that 99% of those points are bad for at least one of the pumps. That means one of the pumps is operating outside of its preferred operating range for 99% of those 28 million. And only one point optimally satisfies demand. And this is what our technology does. This is what the DPO does. It solves all of these millions of simultaneous nonlinear equations in real time to determine the best combination of pumps and speeds to operate at in order to deliver against an operator defined set point. In this case, it's 3,500 GPM. But the DPO does this with 2 parameters in mind. Firstly, it ensures all of the pumps are operating within their preferred operating range. And secondly, it finds the point of minimum specific energy consumption. So by doing these 2 things, we're going to lower the total cost of ownership of that pumping system by increasing the asset life through operating within POR and reducing the energy consumption. And those 2 things, energy and maintenance, make up around 60 to 70% of the typical life cycle cost for a pumping system. So by focusing on those 2 areas, then obviously the scope for optimization is huge. So how does the DPO work? What does it do? So the DPO itself is a small edge device, so a small industrial PC that sits just outside of the PLC. It takes all of the plant data from the PLC, and all of the heavy lifting, all of that computation is done on the edge device. We're able to take it in real time and return it back in real time. That information is also relayed back to our cloud servers. Now, these not only act as an unlimited data historian, but they also configure the information down to our dashboards on our user interface. Now, this can be any web-enabled device. So it could be a fixed workstation inside a control room, or it can be accessed on any kind of mobile device. It could be a laptop, a tablet, or even a mobile phone. So this is the device here. You can see this is an existing control panel. The DPO is installed up here in the top right-hand corner. This is the exploded view, so you can see it. So it's a pretty small device. It's very, very simple and easy to install. It comes DIN rail mounted, so it can be installed in any control panel, and it's got 3 connections. We've got a power connection, we have a data connection to the PLC, and then we have a coaxial cable here, which feeds our antenna so that we can communicate with the servers. So in terms of physical installation, this typically takes around 15 to 20 minutes. One of the key advantages we found as well, particularly over the last 18 to 24 months with the restrictions put in place by COVID, is that we as Pacific Energy do not need to physically set foot on any site to do the installation, the commissioning, or the startup of a DPO. As soon as the device is connected and transmitting data, we can connect to it remotely and do all of that final commissioning and configuration remotely. So we're more than happy to come to site. We like going to site. We like working side by side with our customers. But if geographic or health and safety restrictions prevent us from doing that, we can still do all of that work remotely. We are not impaired by not being able to get onto site. So I mentioned earlier the DPO takes some signals from the PLC. There's certain signals that we absolutely have to have in order for the DPO to undertake those computations. So those signals are on the suction side of the pumps. We need either suction level or suction pressure, depending where the pumps are pulling from. And on the discharge side, we need discharge pressure and discharge flow. We also need per pump power and speed. Now, we can typically get these from the existing VFDs. If you're looking at a pump systems that has fixed speed pumps, we would probably need a power monitor to be installed. But these are the signals that we need: suction pressure or level, discharge pressure and flow, and per pump power and speed. So these are the sort of key benefits. What we're trying to do, as I mentioned earlier, is ensure resilience of supply and give the operators the peace of mind that their system is operating by ensuring that the pumps are operating as they were designed to operate. And we do that by tracking and reacting to the changing pump and system conditions over time. So the DPO uses the computational power to produce real-time in-situ pump curves and real-time in-situ system curves. So we've been able to make our decisions based on actual physical condition of the plant and the system rather than design conditions. We minimize the life cycle costs associated with pumping, as I mentioned, by ensuring we operate within preferred operating range and at the point of minimum specific energy. And then we take that data further and we have an intelligent asset management suite on the back end of DPO, which gives financial information and NPV analysis on current pump condition to enable utilities and pump operation and pump owners to make informed decisions about their asset management and system performance. And you'll see that shortly as we go through the presentation. There's a number of other additional benefits. In the interest of time, I won't go through all of them, but one of the key ones we're seeing become more and more important with our utility customers is the bottom one, is transient control. Now, what transients do, pressure transients are sent out into the system, typically when a pump turns on or turns off, or a valve opens or closes. And these pressure transients, they will go out into the system and they will find the weakest point of the network. And typically that's where you see a burst or a leakage event occur. The key to preventing transients is to ensure that the pump starts and stops are undertaken in a controlled manner, which is exactly what the DPO does. There's a machine learning element to how DPO operates that means that we understand when pumps need to be sped up and when they need to be slowed down. And unlike traditional PID control, where that is just an on-off switch, we do this in a controlled manner over a period of time. So in this particular graphic, you can see here, these are the transients that were sent out into that system when DPO wasn't installed. Same x-axis, same y-axis. You can see under DPO control, everything's undertaken in a much more controlled manner, and we prevented those pressure transients going out into that system. And for this particular utility, we were able to save them around $100,000 per year in repair and labour costs through not having to repair pipe bursts due to the pressure transients going out into the system. So at this point, I'm going to give you a quick sort of run through of the operational and the feel of the platform. Normally we would do this with a live demonstration, but in the interest of time, I'm just going to flick through some screenshots for you. So when I mention a dashboard, this is the dashboard of a typical pumping system. And you can see here, just like your car, it's got all of the relevant information you need to see. So your instantaneous flow, your instantaneous energy consumption, your discharge pressure, tank levels, and which pumps are operating and at what speed. And really, again, what you want to do with a dashboard, just like your car, you don't want to be looking at it 24/7. You just want to look at it from time to time to make sure things are doing as they're supposed to do. And in this instance, we want to make sure that the pumps are operating in their preferred operating range, that the blue dot is in the green zone. And in this instance, this pump station is doing a great job. All of the pumps are operating within POR. Those decisions are being made based on these specific energy maps. And you can see here, these are those U-shaped curves that we mentioned about. These are computed in real time so that we have that actual physical condition and physical efficiency of each pump to make our operational recommendations on. And not only that, we can show you here how operators can have the visibility and the granularity of data and analytics into how their pumps are operating. These are 5 identical pumps. Same model, same manufacturer, same impeller diameter, but because they've degraded, they've worn and torn at different stages over time, they're no longer physically identical. So you can see here by clicking on this bottom U-shaped curve, that's the most efficient pump, pump 3 here. That's able to deliver this flow at a specific energy consumption of around 633. By clicking on the highest curve, pump 5 is the most inefficient pump. That's delivering that same flow, but a specific energy consumption of nearer 700. So that's around 11 or 12% difference in efficiency from one identical pump to another. And this is how the DPO makes its recommendations and quantifies the changes in efficiency over time. We're also able to do that when it's more efficient to switch to 2 pumps slower than just speeding 1 pump up, and likewise 2 to 3, 3 to 4 across to the 5 pumps in the system. So we have full flexibility and control across the entire operational range of that pump system in real time. We take that a step further for each individual pump as well. And you can see here, this is pump number 1. This pump has been operating within its preferred operating range pretty much 100% of the time. These are those operational points. But we can also track the condition of that pump, how it changes over time. As we mentioned before, that light blue line was its factory curve, but this dark blue line was its last tested curve. So you can see the difference in efficiency and capacity of that pump over the course of its operational life. And again, we take that a step further. We're able to, So yeah, we're able to compute this pump curve here in real time. These dark black dots here line up to produce an actual real-time in situ pump curve. And it's this data that we're using to make those operational recommendations. So utilities have the full visibility of exactly how and where their pumps are operating in real time. So it removes that chance and that likelihood of pumps failing or pumps coming out of service without the utilities being able to plan for it. Even further still, I mentioned the asset management reporting. We take that data and every month we produce a monthly report card for each pump station and each pump within that pump station. And we always start off by giving an executive summary of how the pump ran, whether it was in POR, whether it was outside of POR, but also here we're able to quantify the impact on factory capacity, on pump station capacity, which is not something that utilities have typically ever had before. So we're able to say that because of the degradation of those 5 pumps in that system, their current condition, their current efficiency means that if you've got a 100 MLD system, in fact, you haven't now. You've only got a 94 MLD system because there's been a capacity loss due to the inefficiency of some of those pumps. So this is particularly important on clean water and drinking water sites when utilities need to be able to deliver a minimum flow during high demand times. They have to make sure they've got that capacity, and we provide that insight for them. Each pump has its own report card, and you can see here, each pump has a a report on what its current capacity is. So this is a health index of 87, which means it's lost 13% of its efficiency from its factory condition. As a result of that efficiency loss, it's lost 8.5% of its capacity. So we're able to tell each individual pump in the system what its current efficiency is and what its current capacity is. And we take that information, we combine it with some of the customer's financial metrics here, and we're able to give a present value of energy reduction. We subcontract a repair cost off of that present value of energy reduction, and from there we can give a net present value and a return on investment on when and how to change that pump or repair that pump. So we're trying to move utilities away from running their pumps to failure and move them towards running to a positive return on investment. So they will know with our system when the most efficient time to undertake a repair is, and they will also know when they're getting to a point where that pump might cause supply issues or network problems, so they can make that change or make that recommendation for a change before they cause an issue in their network. And I'm going to finish off with a quick case study, just to show you how DPO has been deployed with a particular utility and some of the benefits that, that the system has been able to afford with that utility. So this is Guadalupe Blanco River Authority down in Texas in the US, and this is on their raw water pump station number 2. Now, in fact, this particular utility had DPO installed in around 2015. But due to a change in personnel, they switched it off because the current plant manager felt that he could do a better job. But we still had the DPO installed, so we were still seeing the data. And what we were seeing was that they were operating this system for a flow of around 7,300 GPM. They were running 4 pumps, but they were running those 4 pumps too slow. And you can see each of the 4 pumps was operating outside of its POR to the left. And in fact, each pump was operating outside of POR here around 50% of the time. So huge impact on asset life and huge impact on efficiency for those pumps. That efficiency is quantified here. You can see this is where DPO modeled that the system should be able to deliver that flow at a specific energy consumption of around 1,400 kilowatt hours per million gallons. Where they're actually operating, given they were operating the 4 pumps too slow, was up here at around 1,900. So we spoke to that customer, we told them what they were doing. As it turned out, the guy who'd switched us off had since left and a new guy had come in. He really wanted to use the system. So he switched it back on, and you can see immediately the DPO quantified that pump 4 was the least efficient pump. So it switched that pump off and it sped pumps 2, 3 and 5 up a little bit. So now we've got 3 pumps running a little bit faster, but all of them now are operating within their preferred operating range. So they're now operating within POR pretty much 100% of the time. And the impact in that, in terms of efficiency, is that delta between the modeled performance here at 1,400 and actual is much closer. And the only reason that those 2 dots aren't on top of each other is because during that period where they weren't using DPO, there'd been some degradation of the pumps, which we hadn't yet recalibrated. But what's great about this particular case study is we can demonstrate that at the low flow set point here, on the day that we switched DPO back on, we were able to save them 36% in energy. And as we got to the high flow set point here on that same day, and as the pumps got nearer their best efficiency point, we were still able to save around 8% energy. So harmonized over the first 6 months of operation, we could see that without DPO, comparing it to the time when DPO wasn't installed, that specific energy consumption was around 1,900 kilowatt hours per million gallons. With DPO in operation, that specific energy consumption was reduced to around 1,400. So that's a potential energy savings of around 25% for that utility. In terms of dollar values, that equated to around $265,000 per annum in saved energy for that one pump station. There are a number of other issues that pump station had. We were able to predict suction side blocking on that pump system, and we were able to predict that before the pumps failed. So we saved them both a supply interruption event and repair costs for their pumps. But also we used the digital twin to identify that there was air entrainment and some blockages in the discharge line. So the utility paid around $20,000 to remove those air blockages, remove some of that sedimentation, and it regained around 2 MGD of lost capacity as a result of that. And that 2 MGD of lost capacity resulted in around $735,000 per year in production capacity that was reinstated. So I said that kind of digital twin element of this, to be able to see what's going on in the system, enables us to provide the utilities with the insights to protect their pumps, but also protect their system and ensure they're able to deliver capacity to their users as the design criteria demands. So that's my presentation. I'm open to a lot of questions. I realise we've gone through a lot in a short period of time. So I'm happy to go through more detail if anybody's got any particular interest or any questions. But at this point, I will stop the presentation and open it up to questions and comments and conversation.